Okay, so I think now you can hear me. Okay, so what I was saying is now I'm going to talk about a different talk, a different thing, which is basically related to SPIM microscope. The SPIM microscope here is regarding to the light shield microscope or single plane illumination microscope. And I will make a focus in particular on an instrument that we developed at the LFT with Nick Hede, the sideSPIM. So basically, as Nick mentioned yesterday in his talk, the concept of the light sheet microscope is not new at all. Indeed, it was one of the first, or the first microscope to be able to do fluorescent. And the reason for why is because at that time, at the early 900, it was really difficult to split excitation and emission. And the way that they found is what we know today as a light sheet microscope, they call ultramicroscope. And this technology was dormant for almost a century. And the reason for why is what Nick mentioned yesterday, because basically all the camera-based technology take a lot of time to develop. And basically until 1993, when this came again, or the people rediscovered this technology, and then by the work of Husk and many others, it got spanned to different fields, but in particular to the cell biology. So how does work? Well, we can produce using different strategies, and I will address in a minute, a light sheet, and then we can image with a second objective, basically a full plane with a confocal resolution, or with a theta sectioning. And this has some advantages, and I will cover this. So we already know that basically when we use confocal microscope or wide field microscopy, we excite basically with a Gaussian beam areas which are outside of the region that we want to focus. And in the confocal microscope, what we do is basically we use a pinhole in order to reject the areas that we don't want to see, basically, and focus on our target. Well, with the light sheet, we can do this now because we have a sheet of light, which is basically illuminating a full plane, and we can collect all the photons coming from this plane in a single shot due to camera. This has many advantages. The first of one is the speed, of course, because you can have the full chip of a camera imaging one single shot that can be on the range of millisecond time scale. But the other important thing is we are not illuminating nothing above or below what we want. And this is important for bleaching. So these are the two main advantages. There are different configurations of the light sheet. Basically, we can have double objectives with an orthogonal location. We can have single objective configuration. We can have mirrors, fibers, etc., that can produce this effect of the light sheet and the emission. But how we can produce the light sheet? Well, and Nick already mentioned that we can have cylindrical lens in which we can produce a Gaussian beam, but a flat Gaussian beam, and we can focus this flat Gaussian beam on front of the detection objective, and then we can collect the camera, in the camera. The other strategy can be basically to use a scanner, so a mirror that can move a Gaussian beam across of our scanning optics, so the scanning lens and the tube lens, and at the end we will produce here on the other side, after it passed through the objective, a light sheet or a single plane illumination. So there are different advantages, disadvantages of these two. Of course, this is very cheap because you need only the optics. And in that case, you need the scanner. The scanner usually is costlier than the thing, but the important or the useful thing of the scanner is that, well, for calibration is very easy, because if you stop the scanner, you have a regular Gaussian beam, and this is very easy to basically make the focus with the second objective. The other important thing is that you are not illuminating areas which are outside of the field of view that you are imaging, because you can control how far you want to go with the scanner. And this is not controllable here, it's fixed. So when I joined the LFD, Nick was already, he already built this light chain microscope. It was known as the upright SPIM. And in this case, we placed basically two objectives, one with a low numerical aperture and the other one with a very large numerical aperture, but low magnification. This is a 25x 1.05 numerical aperture. And the reason for why is because we wanted to do a single molecule experiment on this experiment in this microscope. Then we can split in the two paths and recombine them, and half of the chip of the camera will record one color and half of the other chip another color. Or we also did polarization, so it's very nice in this case to accommodate basically polarizers and do anisotropy measurement with this microscope. So here, I don't know if this is gonna work, but this is a small movie that you can see cells doing different things, moving. And you have different dynamics here. You can see, I don't know, paxillin forming here. You can have a cell dividing. You can have a cell migrating. So one of the big advantages of the light sheet is that we can cover all these different dimensions in times with a little changes in the microscope. So we can go to biomolecular dynamics, we can go to cell migration, we can go to cell division or anything, just because this is a very friendly setup that we can cover all these alternatives. Well, the upright SPIM was used in the LFD for a lot of application. Most of these related to single molecule experiment, and Nick did a lot of experiment regarding to the IMSD application, so he can measure the diffusion of a molecule. Indeed, he did it in the two channels, so he did it cross correlation, anisotropy measurement, which is a very nice work on the formation of the paxillin, and you can see there the homofret and how the homofret affect the anisotropy, which is very nice work. And then he did a really large field of view, and I will show how this can achieve. And also he set up an incubator in order to have very long movies of cells and different experiments. So if this is wonderful, why we want to stress or do something different? Well, as I said at the beginning, it has some constraints, or so difficult to accommodate basically this large detector detection objective, and we need to place our sample in some kind of a postal, because the light sheet cannot get on the bottom of a simple chamber. And for that reason, it was one of the main difficulties that we found in order to work in a regular configuration. But also we need to immerse our objective here. And this limits our possibilities in order to use, for example, toxins that can, I don't know, be hazardous for us, or they can distort or broke the optics that we have here. So at the end of the end, we stress our thinking in order to find a different configuration. And the main reason for why we need to change this, it was related to this effect, which is due to the way that we illuminate the cell. So we have a kind of a sagittal view, which restrict the possibilities to do correlation, such as the connectivity map that Enrico introduced the other day. And I hope if I have time, I can discuss a little bit. So one day, Nick come to my office and he said, well, I think I have an idea. And the idea is the sideSPIM. And what he thought is, okay, but if we can have a chamber in which we can have, instead of one window, we can have two windows, and we can put basically the light from the side and image from the bottom. And I said, well, this is a wonderful idea. But he said, well, we have a problem. And I will show in a minute what is this problem. The problem is we cannot get to the bottom because it will screw up our light sheet. Okay, so what is the solution? Well, we found a solution that I think is very interesting and is very friendly to work with cells and with organelles, and this is an interesting thing. So The last thing is, well, we need to design this lateral illumination, and these three things were part of a patent application that we placed a couple of years ago, and now is already set up in the US. And the setup was already covered by Nick, but I will go through very, very fast. We can do single photon excitation. In this configuration here, we were using a white light laser. So we need to basically have different filters. So we have a wheel filter here in order to select the different bands. And then we have some sort of pinhole and other optics in order to clean up the shape of the beam. Then our combination between the two photon and the single photon excitation, our scanner, the scanning lens, and then our objective here, and the emission objective here. So this is a very easy and very cheap configuration to do on an existing epifluorescent microscope as the one that we have here. So where are the problems of the refractivity index? Well, as I said before, if we approach close to the window, in the bottom window, the index of refraction will change from the up and the half up part of the Gaussian beam and the half down part of the Gaussian beam. And this will distort the formation of the light sheet. So for instance, what we need to do is basically put our light sheet, our sample up in the place where there is no problem with this. So what we found in order to do this was basically we can find some supports that can match the index of refraction of the media where we have our samples. And if we do that, this is solved. We basically did some calculation in order to see how much need to be this difference in the index of refraction between the media and the support in order to achieve a proper light sheet formation. And we found that this need to be on the order of 0.3. And trying to find it in the market, different resins that can be used. We identify a couple of them that match this requirement. And lucky for us, the collagen is a very useful biomatrix that we can use for this. And it's also can match our requirement for the index of refraction. So these resins are very simple to work. So here I place a box, and it's very difficult to see here, but this is a resin that we have to place in a different chamber. Of course, this chamber does not work. We can cure with a UV lamp. It's very simple, and we place this resin within a chamber with a 1 millimeter width. And then we jump to the point that, okay, we need a chamber with the two windows, and these were not available in the market. So I remember this day in the LFD, when Nick came to my office, we jumped to the little machine shop that we have there. We make it work the LED. We open a hole in a regular chamber. We glue a piece of glass, and we did the first test, and everything works. And this convinced us that this was the way to go. So then we produce a second generation by the help of Sasha Dvornikov with the machine shop, and you can see here the resin. And after collaboration with Shivav, another postdoc at the Biomedical Engineering, he designed all these different chamber cutting with a laser machine, and it was very simple, easy, and fast to do it. So this is how we look like. We glue a glass in the bottom, and then we glue another two in each side, and then we have each of the chamber. We place some metals and some pins here in order to use magnet to support this pendant stage that is located in the XY stage. And on top of that, we put piezo stakes in order to move really, really fast our sample, because for doing 3D imaging here, we have to keep constant the distance between the excitation and the emission, and we move our sample. And considering that we can move with the piezo, we can go really, really fast. And I will show you this in a moment. So this is the performance of the light sheet in a solution. So we can reach a resolution of 0.7 micrometer. using 0.3 numerical aperture in the excitation beam. And in the emission, we use, depending of the situation that we want to, or the problem that we want to address, but we can go for low numerical aperture to high numerical aperture with long working distance without any problem. So then we did the same calibration on the resin, and this is done basically here, and you can see that when we measure the PSF, we can reach more or less similar full width at Hala maximum that we have in the previous calibration. One problem that we have with the light sheet is that no matter what, we have this effect of the Gaussian beam, and we have basically distortion at the size of the focus, because of course here the Gaussian beam is broader. And this is how it looked like. Well, we have more or less these are beads. You can see that in the center they are very decent focus, but in the perimeter this is worse. So a way to solve this is a develop that Nick performed before, and this is the combination of an electrical lens with the rolling shutter of the CMOS camera. And I covered this at the beginning in the workshop. The first day, I explained that the CMOS camera can be run with a rolling shutter, which means that we can read the lines over and over from top to bottom. And if we coordinate this rolling shutter with an electrical lens that enable us to change the focus in the axial direction easily and fast, we can do what Nick showed here, which is basically we can move the focus of our Gaussian beam across the field of view, and at the same time take the best image that we can with our rolling shutter from the CMOS camera. So this is more or less what Nick found, and he can achieve more or less almost a 1 millimeter resolution improvement with the, of course, the reduction in the resolution in time, because we need to do many images across the full field of view. So I will go to the application. The first thing is, well, okay, but can we place cells on top of our resin? Well, the resin, unfortunately, are very hydrophobic, but if we activate these resins with the plasma cleaner, and then we put PMN and fibronectin, the cells can live and they can move without any problem. These are 3D stack done with the system. And these are cells placed in the inside of a matrix. And I said before that the collagen was a very nice support for our sample. And this is an ideal solution where you want to work in the 3D, because 3D is ideal because we are far from our bottom. So in that case, this helps us to avoid all the issues of the light sheet formation, and it's very good to analyze our samples. So these are, for example, the lamellar bodies labeled with the green fluorescent protein, and you can see the lamellar bodies moving, and these are mitochondria labeled with tamari, and we did many more experiments with a different fluorophore. And this is an example that I like quite a lot, because we image basically the lysosome with lysotracker label for all the lysosome in a cell, considering that we can do really 80 planes with a 500 nanometer resolution in an intervals of 0.2 second. We can basically image all the lysosome within a small time, and this enables us to track all the lysosome in the cell. And this is what we did. This takes a lot of computational effort, because imagine that you have to track all the lysosome in these two cells, and you can see here all the trajectories. Then we calculate the frequency of the velocity for all the lysosome, and this was published in this paper a couple of years ago. But when we noticed that we can go really fast, we stress the system to be used in order to combine the technology with the flow chamber. So to use kind of microfluidic devices. And this is a very nice design because we can go from the top and we can flow solution here. This is a very primitive, I will say, flow chamber. But anyway, it helps us to test. And these are beads passing through the volume, and we are scanning in 3D. And you can see that the up to more or less 3 microliter per minute to 4 microliter per minute, we can recover the 3D without any distortion. And when we go a little bit far, we can see that there is a sniff, which is basically due to the pass of the bead during the 3D stack. But this was important because a collaborator of Nick, Shivav, from the biomedical engineering department, was interested in the growth of bacteria in different support, and also in order to put to use this system to analyze different antibiotics and different molecules that can affect the biofilm formation. So we set up this on top of our microscope, and then he placed some bacteria on top of agar, and then he placed a flow. And what you can see here in the video is the formation of the biofilm over the time. And you can see single bacteria moving around and building up this biofilm over the time with a resolution of 1 second for the whole CT stack, which is very, very nice for dynamics studies. But then one of the important application of the light sheet was in the developmental biology. And in our configuration, the funny thing is, for most of the configuration, you need to basically do a major change or major tuning between the excitation and the emission, because we need to replace one and then match the other and everything. Consider that here we are working with a commercial microscope. The only thing that you need to do is to just turn around your objective for the new one with lower resolution, and then adjust the focus, and then do imaging and pass from the cell to embryos without major difficulties. So this is what we did. We have here zebrafish labeled with night red, which is a membrane dye that can go through the whole animal. And this is the light sheet passing through in the 3D stack. You may see basically different structure, like for example, the muscles, and then you have also the big vessels and veins and the erythrocyte passing through. And I will wait a second in order to pass the CT stack. You start to see these obscure areas here. These are due to the distortion of the image, because when the light passes through to the pigment that this zebrafish has in the skin, is distort completely the light sheet. And this can be avoided, or at least can be solved. Basically, if you, instead of having only one objective of excitation, you can place one from another, and this is already reported in many other examples in the literature. But considering that we can also go really, really fast in these large samples, I found very interesting that we can see, or if we can record the movement of single erythrocyte in 3D across the microcirculation. And this is what we did. You can see here these dark little things passing through here. These are erythrocytes, and we can track this erythrocyte and measure more or less the time that take to go from one place to another and do, I don't know, mean square displacement and all this calculation very, very easily. So finally, we basically decided to also check if we can do this high throughput imaging, and this is something that we are running now. The idea is that you can record one cell, move to another one cell in a chamber with certain condition, then we move to another and do the same, and move to another, do the same, and come back to the first one over and over and over very easily. And one of the good things here is we can reduce quite a lot the volume of our sample, which is very useful when you have to test drugs, which are sometimes expensive or difficult to produce. And you can accommodate here also microfluidic devices that you can replace the sample or change or make a gradient of concentration, etc. And this is something that we would like to keep working in order to development. So considering that I still have like the minute, and I want to stress why we finally designed this. And the reason for why we designed this microscope was to do spectroscopy, and I said before, to do connectivity maps in classical view of the cell, which is in test of the sagittal, basically the horizontal view of the cell. Enrico already introduced the concept of the path correlation, but what I would like to say here is that if we have stacks and we take many of them, and we can do correlation between 2 points, and then we can do correlation of all the points around for all the pixels in the image. And at the end, if we calculate the path correlation, we may see that if we have isotropic diffusion, the image generated by this correlation that we call sprite is homogeneous in all directions. But if there is any kind of distortion for the path of the molecule in one direction or another, what we will have is an anisotropic diffusion, and this will be revealed by this sprite with a change in the shape of the path correlation function in two-dimensional. So to analyze this, what we use is the first and the second moment, and this enables us also to calculate the angle. And then due to these two values, we can calculate how distort is the path correlation function. And this enables us to calculate the eccentricity or either the anisotropy, which are two ways to measure this distortion, and also the angle of the movement. So the concept was already introduced, but is, well, we have some certain eccentricity. If we place a threshold, then we can place a stick, which give you the idea that there is a preferential diffusion in certain direction here. This is kind of a pipe or a tunnel that we draw here, and the molecule only can flow in this direction or if the molecules are bumping here, the average movement will be horizontal, and I will show the simulation in the next slide. So here we don't have labels for our structures. What we are trying to see is if a molecule which is not interacting with our structure can reveal the structure by the information that we obtain from the fluctuations. So this is kind of a method. So, and if we leave this going on, we then can do the path correlation, and you can see that we can capture all the things. This is just a cartoon to show the idea, but if we change the correlation, we cannot do correlation, for example, inside any of the pixels inside this box, because you cannot go more than 4 pixels far, and you will notice immediately that this is an object that is with an imperimetrable barrier. Another interesting concept is the difference between the central moment, which is centered here in the path correlation function, and the center of mass of the path correlation function. And if we calculate this, we can see there is a shift between these two values, and this shift in the center of mass is very useful in order to see the presence of the barrier. So we did some simulation, and this is a channel with 300 nanometer wide, and we fill up this virtually. Well, this is a simulation with a homogeneous concentration of fluorophores, and then we run the experiment, and then we do the calibration, we do the path correlation, and if we look at the path correlation function in different locations, you may see how it's deformated by the fact if there is a barrier or if there is an obstacle or anything. So here is the situation when you are close to the wall, and you may see that you have only half. So the preferential diffusion here will be along the axis. Here is in the center, so all directions are equal. And you can see here that if you move a little from the wall, you can immediately distort, and this is different to this one. So it's very sensitive to really little change. And the distance here is basically the resolution here is the pixel size. Then you can go inside the tube, the pipe, and you can see that the correlation is along as we expected, and in each of the sides is the same of the situation when you are in the wall. So we calculate the centricity, high centricity in the center and in each of the sizes. And if we place a threshold for the centricity, then we can do the connectivity maps. So to test our system, the first example that we thought is, okay, but we need to challenge our system. And a good way to challenge our system is if we have something that is not aligned, that can go around. And this is a GUV labeled with a dye. And if we are able to see the correlation due to the diffusion, the only way that you can see is every pixel should be tangential to the next one, because it's the only way that the dye can diffuse. And this is what happened. We see here the eccentricity, and then we see here the connectivity map without major problem. So, but how data usually look like? And I like to show this because most of the people never estimate what we are seeing when we look the original data. This is original data. I mean, this is what we are using for the correlation. And for me, it was amazing that basically we are looking at very dim information here. This is the background, but still we can obtain very valuable information, which is hidden if you look only at the intensity. These are then the connectivity, and I will show in the next slide using different part correlation how we can achieve different. Oh, yeah, sorry, I have here the movie that if you change the part connectivity with different part correlation distance, you can see different features in the cell due to the presence of obstacles and barriers. This is the same, and then I will stress at the end of this, basically the value of the center of mass shift. And this is the center of mass shift. And the center of mass shift can show you immediately the occurrence of impenetrable barrier. And this is the cell, you can see the envelope, you can see the nucleolar, and then you can see this kind of trabeculated structure here, which we think this is the ER going around in the cells. It's funny because we can see things, but it's difficult to assign to something because we don't have a label for the structure. But anyway, I found very interesting this slide to share with you. So to finalize, basically what I want to say that the sideSPIM solve most of the issues that we have when we start to do this experiment for lower volume, isolation of the optic to the sample. We don't have restriction to access from the top, which is difficult when the upright configuration. We can image our sample in the same plane or the same classical plane that we used to use in the confocal microscope. We can easily interchange different configuration for the sample as well as the objective. And it's absolutely compatible with any other super resolution techniques as you can imagine. So the final thing is, as a future perspective, some of these are already done. And Nick yesterday gave a beautiful talk about this multiple color imaging by spectral imaging using the sine and cosine. And this snapshot acquisition enabled us to image very large area with many fluorophore at the same time using the spectral phasor. Also, we did some experiment we never finished with the film, and they was asking this. Yes, it's very interesting, and it's more interesting to combine film with even spectral imaging at the same time. And we are very willing to try to test all this application for the high throughput. So thank you very much.